Hello, in this video we are going to be covering electrochemistry and specifically talking about voltaic cells. First off, electrochemistry is chemical reactions that involve the transfer of electrons, which is redox reactions. So we have to make sure that we are good with all of our basics on redox reactions before we move on to this video and the following video, because this is really just going to be an application of what we already know about redox reactions. All right, so in an electrochemical cell, we have electrons being transferred, and it will either use an electric current or produce an electric current. Now, we have two types of electrochemical cells, and these are big vocabulary words that we need to know. So our first type, and this is the type we're going to focus on in this video, are voltaic cells. Voltaic cells spontaneously produce electricity. So according to table J, it would be a spontaneous reaction. So when we set everything up, the reaction will occur, there will be a transfer of electrons, and we will produce electricity. So voltaic cells produce volts of electricity. So batteries would be a type of voltaic cell. Then our other type, we will cover these in more detail in the following video, have a non-spontaneous reaction, and those are electrolytic cells. They use electricity to force a redox reaction to occur. So spontaneous, voltaic, produces volts of electricity spontaneously, and non-spontaneous is our electrolytic cell. They have to use electricity to produce the reaction. Again, we are going to focus on our voltaic cells today. Now, voltaic cells could also be called galvanic cells, but more frequently you're going to see them referred to as voltaic. Again, they produce electricity and they do occur spontaneously. If we were in school, we would do a lab with voltaic cells and we would set everything up like this. So we would have two beakers, two pieces of metal, this little U-shaped tube. We'd have solutions in each beaker. We would set it up and attach it to a voltmeter. The voltmeter would measure the voltage that is produced by the reaction. So we would actually set something up that would look very, very, very similar to that and measure the amount of voltage that was being produced. We're obviously not going to be doing that this year, but we will talk about all of the parts of this diagram and talk about how we would set this up in lab. Before we get to the specifics, one other thing that I want to briefly mention, some of you may have seen something like this potato clock. This works off of the same principles. You have the metals, those are our electrodes, they're connected by a wire. It produces enough electricity in order to run the clock. So this is just an application of a voltaic cell. Okay, so if we look back at that picture, we had two beakers. Each one of the beakers are a half cell. It is half of the cell, and you have a half reaction occurring in each beaker. So each beaker has some solution in it. Each beaker has reduction occurring. Your two half cells are connected by a salt bridge. So a salt bridge is literally, remember, salt means ionic salt, so it literally is an ion bridge. It allows ions to flow back and forth between the two beakers. So that was that U-shaped tube. The ones that we would have used in lab are made out of glass. We would fill a solution, or we would fill it with a solution, and then we would put a teeny bit of cotton in each end in order to keep the solution in. We would put a teeny bit, because if we put too much, then that would block these solutions from mixing, and we need that to happen. So it allows for the transfer of ions. So ions flow back and forth between the two cells. So salt bridge allows the flow of ions. Very, very, very common multiple choice Regents question. All right, in our setup, the pieces of metal that are in each beaker, those are the electrodes. So the electrodes are actual pieces of metal. So aluminum, zinc, copper would be some common ones. So we've got our salt bridge between here, and then we'd also have a wire between the two metals. So your electrodes are pieces of metal. They are solid because they are actual pieces of metal. Their oxidation number will always be 0 because they are the solid metal in its elemental form, not part of the solution. And then we have names for them. So we have the anode and the cathode are the names of our two electrodes. The anode is where oxidation occurs, and the cathode is where reduction occurs. And that is something that we will need to memorize. So again, anode is where our oxidation occurs, and cathode is where reduction occurs. Now, you know how in a battery we have a positive end and a negative end? Same type of idea here. The anode is going to be the negative electrode, and the cathode will be the positive electrode. Now, a couple of different ways to remember that. Anode has N in it, so that can help us remember that that's the negative electrode. Cathode, when we write it out in lowercase, the T kind of looks like a plus sign, so that can help us remember that it's the positive electrode. One additional way to remember this, earlier in the year we talked about negative ions are called anions and positive ions are called cations, so that can help you remember it too. Then we got one of these little sayings here. We got red cat and anox. So red cat is reduction occurs at the cathode. Anox, oxidation occurs at the anode. Another way you could remember it is you're partnering up your vowels and partnering up your consonants. All right, so normally when we have a reaction, and we're going to take a look at one in a second, we write out our half reactions, we figure out what's being oxidized, what's being reduced from the half reactions. The metal that's associated with the oxidation would be the anode. The metal that's associated with the reduction would be the cathode. Sometimes they don't give you a reaction. If that's the case, then we would use table J to determine which is which. And whichever metal is higher on table J is the thing that would get oxidized, therefore it would be the anode. So for example, let's say that we were given some different materials. So we were given zinc metal, aluminum metal, then we were given zinc and aluminum solutions. So let's say we had zinc nitrate as one of our solutions. So that would be aqueous. And we had aluminum nitrate as our other solution. And what is going to be the cathode? They have to be solids, so it has to be the metals, the zinc and the aluminum. Normally you would have the reaction, you would write out the half reactions, whichever thing's being oxidized, or whichever metal is being oxidized would be the anode. The metal associated with the reduction would be the cathode. But if they don't give us the reaction, we look on table J, and whichever metal is higher we'll be losing electrons easier. Loss of electrons is oxidation. Therefore, whichever metal is higher on table J would be the anode and be getting oxidized. So that would be aluminum, and then zinc would be the cathode. All right, one other thing before we get to our example, the electrons flow through a wire. Electricity flows through wires, so that should be easy to remember. And the electrons flow from the anode to the cathode. So they go through alphabetical order from the anode over to the cathode. Now, the reason why the cell produces electricity is because there is a difference in electric potential between the two metals, the two electrodes, and the system will try to reach equilibrium. So electrons will flow from the anode to the cathode until equilibrium is reached. Once it gets to equilibrium, then the cell's voltage would be 0. And the further apart the two metals are on table J, the more voltage they will produce when they are set up in a cell. If it's a reversible reaction, once it gets to equilibrium and the voltage is 0, then the reverse reaction would occur that would rebuild up the difference between them. And then once it's recharged, then the forward reaction can happen. So cell phone batteries are obviously rechargeable. So they're doing the forward reaction, producing electricity. Then when the battery is dead, you do the reverse reaction, which is not spontaneous. You have to plug it in order for your cell phone to charge. That builds up the difference in electric potential again, recharges it, and then the forward reaction can happen once again. All right, so now we're going to take a look at an example. So if we were given this reaction and asked to draw the electrochemical cell, first thing we would do is go through identify oxidation states and write out our two half reactions. So zinc would be 0, copper would be 0. We could do the sulfate ion, altogether would be -2. So then copper would be +2 and zinc would be +2. So sulfate would be our spectator ion. Okay, so one half reaction, zinc 0, solid, goes to zinc +2, aqueous, and 2 electrons. My oxidation number is increasing, therefore this is the oxidation. Oxidation will always happen at the anode. And the anode will be our negative electrode. My other half reaction would be copper ion +2 electrons goes to copper 0, solid. So throughout this reaction, we'll be producing the solid. So the mass of the copper electrode would actually increase during the course of the reaction because we're producing it. The mass of the zinc electrode, the anode, would decrease over time because we are consuming it. All right, that's a reduction. Reduction always occurs at the cathode, and the cathode will be our positive electrode. Okay, so if we had to draw our diagram, you would draw your two beakers. We're going to add some solution to our beaker, and each one of our beakers is going to have a metal in it. Now, it doesn't matter which side we put the anode on, if we have that one be the anode or that one be the anode. It obviously doesn't matter because in real life, you can obviously move the beakers. You know, they can switch spots. It doesn't matter if they're on the right-hand side or the left-hand side. Let's just say we have this first one over here be the anode. So if that one is the anode is where oxidation occurs. So we need the solid associated with the oxidation. So have to put the zinc sulfate solution. So this is where zinc metal would be and the zinc sulfate solution. The anode is the negative electrode. Okay, other side, this would be the cathode. And the cathode is where reduction occurs. So we need the solid associated with the reduction. So the cathode would be a piece of copper. And the cathode would have a positive charge because the cathode is positively charged. And then in this beaker, we would pour in the copper sulfate. So the copper solution goes with the copper metal, the zinc solution goes with the zinc metal. We would need to put in the salt bridge. So salt bridge allows for the flow of ions between the two beakers. And then we would need to connect our two metals with a wire. If we wanted to measure the voltage being produced, then we would have to connect the wire to a voltmeter to measure the amount of voltage that was being produced by the reaction. And then again, a couple of things. The zinc metal would be getting consumed, so that would decrease over time. The copper is getting produced, so the copper would increase over time. So we still have conservation of mass, but one's going to get a little smaller, one's going to get a little heavier. And then this basically just shows us all of those things that we just filled in. Oh, one thing that I forgot to say was you would have the half reactions occurring in each one of the beakers. So the zinc metal would be dissolving, turning into the ions, and the copper ions would be combining with the electrons to turn into the copper metal, and electrons would be flowing through the wire from the anode to the cathode.